Okay, let's take a look at something called the level range formula. It is a useful formula, at least sometimes. As is typical in physics, you need to understand that some laws and some equations actually have limits to their range, if you will, of acceptability, and you need to understand what those limits are so you know when to use the formula and when you cannot. If, IFF, that means if and only if there is no overall elevation change for a projectile, the range formula can be used to relate the launch angle, launch speed, and the total horizontal range. So this formula that we'll develop is applicable only when a ball is maybe kicked or thrown and it lands at the exact same spot from the elevation that it was launched from or thrown from. So some obvious applications here. A soccer ball being kicked from the ground and then landing after it's traveled as a projectile back on the ground, we could use this formula. A football, maybe a punter kicking the ball at maybe chest height or a little bit higher, and the ball travels through the air, and the punt receiver catches the ball again at the same elevation from which it was kicked. We could use that formula. If we're a basketball player and we shoot a three-pointer, probably can't use the level range formula because the ball is going to go through a net that's at an elevation of 10 feet. Unless the person shooting the ball jumps up to that elevation, more than likely there's going to be an elevation change and we cannot use this formula. Let's go ahead and develop it. Here it is. R is equal to V naught squared sine of 2 theta all over G. I want to show you where that equation comes from. So on any kind of projectile motion problem, the typical way to do it is to resolve some initial velocity usually given as some magnitude at some angle, resolve it into its two components. So let's go ahead and do that. Let's use green here to represent the horizontal velocity, v naught x. That would be equal to v naught times the cosine of theta. And we could just as well resolve that velocity into its vertical component as well and find that v naught y would be equal to v naught times the sine of theta. And you've certainly seen this before. Now, as the projectile travels through the air, we know that it would be through some sort of parabolic arc. By the time it hits the ground, some distance r away, it will have had no elevation change, and that's key to using this formula. So that means delta y over here is 0. It certainly rose up to some higher elevation, but by the time it landed, it had no overall elevation change. Now, we're interested in determining how far this thing will travel. Again, typically how we do this is we solve for motion, solve for time in one direction, and then use that time in the other direction to be able to determine that final answer. Here, we know enough information to come up with an expression for time using the y velocity. Let's go ahead and do that now. So in the y direction, we're not going to be able to solve for that value, but we can come up with an expression for it. We know that by the time the ball rises and falls, it has no overall elevation change, but I also know that its vertical velocity downward at this point, v naught or v final y, is exactly the same size as v initial y, just in the opposite direction. That will allow us to come up with an expression for time using this equation. It's one of our famous equations. It's equation number 1 on my list over on the board. Here, I know that my final velocity is negative v naught sine theta. My initial velocity was v naught sine theta. Now we're going to call downward negative, since we call this a positive value here. That means that this would go in as a minus g times t. I'm interested in the expression for t, so let's go ahead and isolate that variable. Negative v naught here, I'm going to subtract v naught from both sides, and I get negative 2 v naught, of course I have that sine theta in there, is equal to negative g times t. Divide both sides by negative g, and what we get is that our time is equal to 2 v naught sine theta all over g. An expression for time, all solved in variable form. Now let's go ahead and take that value for time and plug it into my x equations to determine how far it will travel. Let's switch that over to blue. And when we do that, we got r is equal to v naught x multiplied by t. There's no acceleration that way. And so v naught x would be v naught times the cosine of theta. Multiply that by that expression for time, which would be 2 v naught sine theta, all over g, and we're getting pretty close. We can see that that's really close to this here. We just have to use a trig identity, and that trig identity is this. We know that 2 sine theta cosine theta is equal to the sine of 2 theta. So this trig identity is going to be used to clean this equation up a little bit. Here I see a 2, here I see a sine theta, here I see a cosine theta, and so I can replace that with the sine of 2 theta. I see I got a v naught squared times the sine of 2 theta all over g. And so that equation, cleaning that up, gives us the level range formula. And there we go. Not too bad. The cool thing about using this formula here is that since we solved this all in variable form, we can use this for any velocity, for any angle, for any place. If we're on the Earth or if we're on Moon, you got it. We have an expression for the range using just the variables that might be provided to us. We do have to be careful here. This is not a resolved velocity. V naught is not V naught x, it's not V naught y. It is the original velocity squared, multiplied by the sine of twice the angle. If the soccer ball is kicked at a 20-degree angle, this would be the sine of 40 degrees. We have to be careful with that. That's some of the details of that equation. OG, the other thing, is that we called G 9.8 meters per second squared. We defined it as downward right here with that negative. We don't put in a negative value here. We put in 9.8. We would not want a negative range, which is what we would get if we put in a negative value there. So we took care of that downward direction right there. That value there is a positive 9.8 meters per second here on Earth. Now this formula states that for a given launch speed, there are actually 2 angles that will provide the same horizontal range. It's a little bit of a mathematical principle to know that there's 2 angles that will give us the same sine value. Let's go ahead and take a look at that using a unit circle. If we have an angle theta, I'm going to zoom in here a little bit so we can draw this more clearly. If we have an angle theta, let's say it's right here, 20 degrees or something like that. If that's theta, then this would be 2 theta. And so this would be 2 theta. That value right there would give me the sine of 2 theta if this were like a unit circle. We know that there's another value for 2 theta, or another angle rather, that will give me the exact same value, and that's over here. And so if this is 2 theta, this would also be 2 theta. And you can see that, let's see, these 2 angles are actually supplementary. So that means that the actual value theta would be complementary. The 2 angles that will provide us the same horizontal range are complementary. That means they add to 90 degrees. Yes, that's stated right here. Also, the maximum range is obtained when the launch angle is 45 degrees. If we put in a value of theta to be 45, then 2 times 45 is 90. The sine of 90 is maximum at 1. So the maximum range of a projectile is V naught squared all over g, and that would occur when the angle is 45 degrees. Now I want to pull up a quick little simulation and show you that. And so here we have our PhET simulator. Just open this up really quick, and hopefully you've had a chance to maybe play around with this a little. If not, this might be a chance to observe this cool simulation. Let's just do a 30-degree angle here. If I shoot this thing out at that particular angle, we see that it lands at that spot. The complement to 30 is 60 degrees. So let's take the thing up here to 60 and shoot it as well. And you can see that sure enough, it lands on the same spot. If we were to go, let's see, 40 degrees, you can see 40 takes us further away. The complement to that would be 50 degrees. And sure enough, you should see that those land at the same spot. And the maximum angle, or the maximum range, would occur at 45 degrees. And you can see that that got out there just a little bit further. So there we go, some complementary angle ideas, very useful outcome of that level range formula. Let's go ahead and just try a couple of examples. A soccer ball is kicked at an angle of 18 degrees to the horizontal, landing 52 meters away. No elevation change here. At what velocity was the ball kicked? We're going to assume negligible air resistance, which again is a requirement for us to use this equation. Let's go ahead and just draw a quick little sketch here. So we got a ball being kicked, 18-degree angle. We could probably obtain that information from watching maybe a video of that ball. We don't know the speed we want to find that. It comes over here, lands some distance away. And that range here, we said 52 meters. Level range formula works. There's no elevation change. What was the speed of the kick? Let's start with the level range formula. And I'm looking for V naught, so let's see, V naught squared would be equal to R times G divided by the sine of 2 theta. Take the square root, and we get that V naught is just very simply computed. It has 52 meters multiplied by 9.8 meters per second squared divided by the sine of twice that angle. Now twice of 18 is 36 degrees. And when we go through and do that calculation, you get an answer of about 29.4 meters per second. And we could certainly round that to 29 meters per second if we'd like. There we go, quite easily determined using the level range formula. Now over here, what if we wanted to get the ball out to a greater distance? So instead of 52 meters, we want to increase that range a little bit. What angle would we need to kick? So let's see, let's redraw that here. It's going to have to be a little bit steeper angle, and I know that because the maximum is going to occur at 45 degrees, and since we need to get further, we're going to get closer to 45 here. Don't know what that value is yet. We'll find that out here shortly. So what is that value of theta given the initial velocity is 29? I'm going to go back to the 0.4 meters per second. A little bit more precision. I'm not drawn to scale, but if we want to get this out to 65 meters for that range, we can do that using the level range formula. So again, we start with this. Just solving for a different variable here. So the sine of 2 theta would be equal to R times G divided by V naught squared. So 2 theta would be the inverse sine of that. And let's plug in some numbers here. The range for this problem now is 65 meters. We're going to multiply that by 9.8 meters per second squared, and then divide that by 29.4 squared. Take the inverse sine of that to be able to get 2 theta, and I'm getting about 47.5 degrees. I'm interested in theta. Now we divide by 2 to get that value, and that's about 23.7. Let's round that to 24 degrees. Oh, important side note, that's only the shallower angle that'll get us there. If we wanted to instead kick the ball nice and high and get it to that same spot, we would have to then find that by taking the complement of that angle. So 90 minus 24 is 66 degrees. And so that angle would also get us there. Now, important to note, your calculator will not give you this one. Your calculator is going to give you the smaller of those two angles. You'd have to think through to figure out that other one. What if we wanted to determine the maximum range of that ball? Could certainly do that right here. So what is the max range? And that max range would be and when you go through that math, you would get it to be about 88 meters. There we go. Level range formula, very useful at times.